Hello, everyone. I'm Losey, a postdoctoral scholar at Stanford University. Our research group is interested in how human teams can perform collaborative tasks, like the one you see here, where you have two people moving a chair up the stairs. One way that these people can collaborate is through explicit communication. We can talk to one another saying where we want to go or how we want to move. But humans use more than just explicit communication. We also use our forces and torques, guiding one another away from the wall or up to the stairs. So in this talk, I want to focus on how robot teams can leverage implicit communication to solve collaborative tasks. Like this one. Here we have two robots that are, like the humans in the previous slide, decentralized. They have separate controllers that they're using to make decisions. These robots are holding a metal rod, and they share a common goal. They want to take this rod and place it down on the table. While they have a common objective, they have different information about the world around them. The robot on the left sees this pile of boxes. By contrast, the robot on the right sees this pile of books. In reality, both obstacles are there, and the robot should move to avoid them both. One naive solution we might use to solve this problem is independent control, where robots make decisions based just on what they see, and they ignore their partner's actions. When we use independent control, this is an example of the plans we come up with. The robot on the left wants to move in front of the boxes, while the robot on the right wants to move behind the books. In practice, this doesn't work out. The two robots are trying to move in different directions, their forces counteract one another, and they end up moving right down the middle, smacking into the boxes that the robot on the left saw the entire time. Why did this fail? Why did the robots not successfully collaborate during this task? I would argue that the robots failed because they did not harness the implicit communication or information that was available within their partner's actions. We argue that when robots share control, communication is often necessary. Look at the slide that the video we just saw in the previous slide. And humans do this communication, not only via words and speech, but also implicitly through our actions. And I argue that robots should be able to do the same. So in my talk, I want to first formalize shared control as a learning problem, where I can take my partner's actions and learn from them about what I cannot see in the world around me. I also want to introduce roles, which we can use to enable implicit communication via actions. And then finally, I want to explain how these roles work, both in theory and in practice. So let's start off by looking at the formalism. This is a jointly fully observable system. The state is shown on bottom, and it consists of the configurations of both arms and the position of obstacles in the world. But neither of the robots sees this entire state. The robot on the left just sees its own configuration and these pile of boxes that are close to it, whereas the robot on the right sees its own component of the state, S2, as well as the obstacle that's closest to it. Of course, I don't just see the state, I also see my partner's actions. And ideally, I would take my partner's actions and make decisions using both those actions and the state that I'd see. I'd come up with a decentralized policy, kind of like the one shown here. Intuitively, you can think of it as, I don't see the entire state, but my partner's actions might tell me something about what I don't see. If I could harness that information, I could then make decisions to avoid these obstacles. And this leads to the core problem that our group ran across, which is interpreting our partner's actions is actually really hard. There are so many different reasons why our partner might take one given action that inverting that action to then learn from it becomes a real big challenge. To give an example, consider the scenario shown here. We are the robot on the left, and we see our state, and we see the action that our partner is taking. Now, the partner is moving slightly to the right, and if I were to assume, hey, the reason you're taking this action is because you want to exploit what you see in the world around you, I might assume that there's some books right beneath your robot arm. What if I were to instead assume that my partner is actually trying to actively give me information about the world? Maybe they're moving to the right in order to show me that there is a pile of books over there. Now it's the same action, but I think the books are in a completely different place. Or a third explanation might be that there's no books to begin with. My partner is actually taking this action because they want to gather information from me. They're perturbing my behavior to see how I respond so that they can then learn about the position of the obstacles I see, these boxes. Let's make this slightly more formal. This is my decentralized policy. I make decisions based on the state that I see and my partner's actions. If we break this decentralized policy into parts, the first is a centralized policy. Now, this is what I would ideally do if I could see the state that my partner sees, S2, but I don't. Instead, I have a belief over this unobserved or latent state. This belief consists of, on the far left, sorry, in the left of the two new terms, a likelihood function, which tells me, based on the action my partner takes, how likely is this unobserved state, as well as some sort of prior over this state. So putting it all together, I'm making decisions that would try to match the centralized policy, but I'm learning about this state I can't observe from my partner's actions. And what you might notice in this previous slide is that the likelihood function I'm using to learn from my partner is actually my partner's policy. And my partner's policy relies on my policy, while my policy, again, relies on my partner's policy, so on and so forth. This is actually a pretty well-studied problem in the context of theory of mind and human-robot interaction, which leads to infinite recursion. I have no idea how to interpret my partner's actions because their actions depend on my actions, so on and so forth. Putting this into language, what do you think, I think, you think? The insight that we used to resolve this issue is that we broke the team into roles. Now, what these roles did is they provided a structure to interpret the meaning behind my partner's actions so that if I know what role my partner's using, I can correctly interpret the meaning behind or the reason why they're taking these actions and learn about the system state. I want to emphasize that these roles aren't specific policies, but they're actually a class of policies. One would be this speaker role, where you make decisions based only on the state that you observe. We would pair this speaker with a listener. Now, what this listener does is kind of what I've described so far. It makes decisions based on both the state it observed and its partner's actions. But the key here is that I know, when I'm the listener, that my partner is a speaker, and they're making decisions based only on what they observe. So I can now infer from those actions what's going on in the state that I cannot see. In order to better understand these different roles and how they work, we looked at some simple settings just to get some sort of baseline understanding. Specifically, we looked at controllable linear team dynamics with linear feedback. And we found 4 interesting properties. The first being, if I have these roles, so I have a speaker and a listener, can I always be the speaker, or do I need to switch? Turns out, yes, you definitely need to change roles, or else your team can become unstable. Okay, great, I need to change roles, but how should I do this? We actually have a theorem in the paper that suggests that one good way to change roles is actually having some sort of predefined frequency where I'm going to switch from being the speaker to the listener every second, or 10 times a second. And as the rate of switching between speaker and listener increases, my decentralized team, where we're only communicating via actions, actually approaches the behavior of a centralized team, where the agents both know the entire state. Another really cool question that we saw was, when you're the speaker, what do you do? Like, what's a good action to take as a speaker? Well, you should definitely exploit the world around you, but actually, we found that effective speakers do more than that. They also exaggerate their motions. They take legible actions so that their partner can more clearly see what they're seeing, more clearly learn from their actions. Okay, great. So all this was in a linear setting. Let's go back to the non-linear setting that I originally posed, where we have 2 robots. I want to just briefly mention that this problem is different from multi-agent reinforcement learning because I don't have any offline demonstrations or training or data. I'm trying to solve this problem all online during the current task based just on the information I'm gaining from actions. So here are the 2 robots and what they ultimately come up with when they are changing roles during the task. They start by moving, again, straight down towards the obstacles, but based on the forces that their partner applies, they recognize, oh, there's an obstacle here, or there's an obstacle here. And so they both move together to the left, successfully completing this task and avoiding the obstacles. If we compare the original video that we saw, where the robots solved this task independently, we see that those robots were resisting one another. They were trying to move in different directions, and they were applying this internal force that prevented them from succeeding. But when the robots change roles during the task, this internal resistance force disappears. The robots align their actions, move in the same direction, and successfully coordinate during the task. I also want to briefly mention some simulations that we did. These simulations were in a game setting where we had 2 robots that were trying to move a table from some start to a goal. There were a variety of obstacles in the world that the robots needed to avoid, and we compared it over, I think, 1,000 randomly generated games. And here we're looking at success rate. How frequently did the robots make it to the goal within these randomly generated worlds? So higher is better. We considered a spectrum of different types of communication. On the far left, you see an explicit communicating team, which is sending messages to one another saying, oh, this is where this goal is, or oh, this is where this other goal is. Now, at the other end of the spectrum are teams that have fixed roles. I'm either always a speaker or always a listener. And then sort of between these two extremes along the spectrum is this team that communicates by changing roles. And these teams are changing roles either maybe once every time step, once every 4 time steps, so on and so forth. And what we saw that's interesting here is that teams that change roles actually are able to achieve about the exact same success rate as teams that explicitly communicate by sending messages. So roles can be quite effective. Just using actions and the information that's contained within actions can be quite effective as a learning tool during these collaborative tasks. So all that's great. What are some of the limitations for this work? Well, to think about these limitations, I want to draw you back to the motivation I originally gave where we were considering a human-human team, or even a human-robot team. What we have mentioned so far works really well for robot-robot teams, but how do we then take what we've learned and use it on human-robot teams? I think there are 2 main challenges that we've been thinking about. The first is, okay, we've sort of identified what these roles could be for robot-robot teams, but what roles do humans actually use? And then we know that we want to change these roles during the task. How do we influence the human to change what role they have? Maybe how do we encourage the human to learn from or listen to the robot? I want to point you guys towards some recent work we've done on this first challenge in which we've tried to figure out better ways to enable humans to be speakers and convey their understanding of the world. We did this work in an assistive robotics setting where the person is trying to teleoperate a robotic arm, guiding it to complete a cooking task. They're using just 2 degree of freedom joystick, but the robot's moving in a high dimensional space. So we need to be able to learn, how do I map this low dimensional input correctly to these high dimensional tasks? And this is one way that we can help robots listen to or use humans as effective speakers during collaboration. So to summarize, I hope I've convinced you guys that there is valuable information contained within actions. And good robot teams should learn from and leverage this information to solve coordination problems. I've mentioned how we can use roles to help address this challenge by breaking the infinite recursion of what do you think, I think, you think. I've also mentioned some theoretical and experimental results that we've used with these roles. So with that, I'd like to thank you all, and I'd be happy to take any questions.
Can we turn on the microphone?
Hello. So you mentioned you compared explicit communication to this communication through actions. I was wondering how you did the explicit communication, because it would seem you could implement centralized control if you do explicit.
Yeah, that's a great question. So you're asking about how we implemented the explicit communication in the simulation I just presented. What we did is we had each agent would send a message to their partner saying, this is the location and the geometry of the nearest obstacle that I see. We compared sending this every time step, every 4 time steps, so on and so forth. I think this is one good way that you could do explicit communication. At the very far end of that spectrum, not shown, would be a team that's fully centralized, that both sees the entire state, the entire task. That was kind of like a baseline across all of these different simulations, and those people, or those groups, were successful 100% of the time, because they completely knew the world they were operating in.
Okay, thanks.
Thank you.
I understand the motivation in the context of human-robot team, but when you have 2 robots, wireless Ethernet is relatively cheap to robotic arms. But still in that context of communication, there are other important issues, like the state that each robot sees may be slightly different relative to the other. Why not focus more on these aspects in the context of robot-to-robot team?
Yeah, that's, again, another question, and I think something that most people kind of wonder about. So I think there are 2 answers. First is, like I mentioned, we have this motivation of working with human-robot collaboration during these tasks, and we want to be able to use the information in my partner's actions to communicate. So we dream of a system where the robot uses its actions to clearly show to my partner, hey, I'm moving to the right, or oh, you should tilt the table on its side. I think that's one example. The other one would be that although, yes, you can use explicit communication, why would you throw away the information that's already contained within actions? You could use them both, right? You could send messages to your partner and also use their actions to learn even more, or maybe reinforce the information that you've learned through these messages. So I don't think it's mutually exclusive if you're just looking at robot-robot settings. Finally, there are some tasks that are inherently decentralized. One might be autonomous driving, when you have many, many cars on the road. Perhaps they're not all controlled by a centralized system, and it might be good for them to, oh, because you're taking this left turn here, I can infer that you're gonna like move to the left or speed up or something like this. So I think there are contexts where decentralized control does come up, but it is more rare than a coordinated centralized policy. So yeah, thank you. Yeah.
So, so my question is, do you actually observe the actions here? Because fundamentally, aren't you observing like the measured force and you have to infer the action? And doesn't that add uncertainty that's not being handled directly in the formulation that you presented?
Yeah, thank you. That's a really good question. So the actions in the context that I presented actually were those forces and torques that my partner applies to the metal rod. So we are treating those as the actions, but you're completely right that our observations of these actions are noisy. We don't perceive exactly the force they apply. We maybe perceive it with some Gaussian noise or something of this sort. In the paper, we kind of explored how do we deal with this noise? And we found that in the linear cases, it's actually fine to act as if this noise is the real robot and then just work with it. Because as long as the noise is unbiased, the team still converges to the centralized behavior. But I do agree that in practice, you do want to consider maybe how do you measure these actions? Do you have a good sensor for measuring these actions, et cetera? So yeah, really great question.
How do you distinguish between your partner's actions and just external perturbations?
Just to follow up, would you mean like maybe something else completely collides with
Like
the obstacle?
If you do collide, how do you know that this collision is going to create a force? How do you know that this force is from your partner or from the obstacle?
Yeah, another really great point. I think in the example that we brought up, we would probably want to use vision to understand where these, maybe if there is an external perturbation. But you are correct in that if I have no way of knowing whether this is an external perturbation or my partner's actions, I might incorrectly interpret that as an action and try to learn from that. That is definitely a limitation of this approach, and you would want to have some sort of maybe a filter or a camera to sort of distinguish between maybe a high frequency impact and a low frequency correction. But yes, that's a really great point. Thank you.
Great. Let's thank the speaker again. And now